I first of all thank the organizers for giving me this opportunity to come to this place. It's a new institute. I haven't been here before. I have been to Bangalore many times, but this is completely new. In fact, while coming at night, I was a bit afraid where I am going. I was suddenly, the road changed to some place where there was no people, no locality, and yeah, but this is a fantastic place. I'm overwhelmed to see all the infrastructure and everything. And yeah, it's a nice meeting. I'll miss the next 2 weeks. I'm a bit sad about it because it's a semester is going on, the teaching responsibilities. But yeah. So today, this talk is based on joint works with Parthanil Roy and Ayan Bhattacharya, who is his PhD student. He has submitted and got his PhD, and now going for a postdoc in Netherlands. So this is a bit. We finished this work about 1.5 years back. But since now both the works have been accepted and published, it's kind of time to again go back and revisit things. So the talk will have kind of 3 sections. So I'll be talking a bit about the history of the problem, about extremes of branching random walks, and then I'll go to the setting which we are working in. Although I have written it's a dependent heavy-tail branching random walk, I won't be talking much about the dependence because it might take away the flavor of the problem. I'll tell what it is. And in the end, I'll come to something called stability, which refers stability of point processes. So it will refer to some kind of it will be an analog of the stability of random variables in the words of point process. And we'll touch upon what is the famous Brunet-Derrida conjectures for the branching Brownian motion. So what is a branching random walk? This is a verbal description. So it's a natural extension of a Galton-Watson tree in the spatial sense. So what we start with one particle at the origin, and the first generation, so one particle is generation 0, then the particle splits up according to a point configuration on the real line. So it's a point process on the real line, and you see some points on the real line, and they form the children for the first generation. Then each particle of the first generation again reproduces with respect to this point configuration independently of the other children, and you go on with this process. And I'll come to this pictorial description of what do I mean by positions. And each individual of the nth generation, you go on doing this process, produces independently of each other and everything else. So here is a picture to understand what is happening. So you're given a point process L. You start with one particle at the origin, and then say it splits up into 2 particles according to, so here it's 2. Then in the next time, 2 of these split up into, say the first particle splits up into 3 particles, which you place, I think of this on the real line out here, and this one splits up into just 1 particle. The important thing to note here is the term displacements. So what do I mean by displacements? If this is the position, if I just project the position of this first generation particle on this line, this part means the displacement of this particle with respect to its parent. And similarly, this is a kind of a negative displacement on this side with respect to the parent. And if you see, the third child also has this displacement. And this one came down straight, it has displacement 0. So these are the displacements. And I will call these points to be the positions of the particle. So one thing to know, if you know the displacements, you know the positions. If you know the positions, you know the displacements. So when we go further into the mathematics of it, we'll impose some conditions on the displacements of these random variables. So this is the structure which goes on. So what we are interested in learning is the point configuration in the, say this is the nth generation. After the nth generation, these are the positions of these particles. So we want to study in the large time scale how the positions of these point configurations converge in certain sense. So we'll have to put in certain assumptions on the displacements on the tree. So first of all, so what is the tree? The tree structure turns out to be a Galton-Watson tree. So we'll put in various assumptions on the displacements and also sometimes also on the positions. The question of interest, what this talk is about, is we'll look into, say, the particle V in the nth generation, and we'll look into SV, the position of the particle. We'll rescale that SV with certain, say we'll center them with Bn and rescale with An, and the delta notation is, delta of that point is 1 or 0. So it's a Dirac delta notation. So we look into the point configuration of the nth generation out here, and we ask how does this point configuration Nn or the point process behaves as n tends to infinity. Whether it converges to something and whether we can explicitly characterize it, whether we can identify the limit properly. Now, another interesting question which was first studied, or like it came up most important.
So you do not want to normalize
No, not this sum, but when we look into the configuration, like we'll normalize, like this is the normalized positions.
Okay, the positions are normalized,
not the sum, but the positions are normalized. No, it's a limited. So we'll assume these are all real valued, or this line you saw are all real valued. And so another interesting question is, if you look into the nth generation, what's the topmost particle? Or if you rotate this picture, what's the leftmost particle or the rightmost particle of this? Where does this converge? And it's clear that if you have an answer for the whole configuration, then this answer comes out automatically out of there. Because you know the whole configuration, so you'll know the rightmost particle or the leftmost particle in that. So how did it all begin? So although this talk is not related to branching, so Brownian motion, but maybe it's better to recall like how all this started, and just to put in position, so just to put in where our work stands. So the work first started is with branching Brownian motion. Branching Brownian motion has an exactly same type of dynamics I described before. You at particle, say you at time 0 you start with a particle 0 on the real line. Then the particle moves, one particle moves, so the first one, it's not very clear, makes a Brownian motion up to exponential time, and then it splits up into 2. And these two Brownian motion again perform, these two particles again perform Brownian motion up to exponential time, and this goes on. And at time t, you again look into the positions. So a brief calculation shows that there are like exponential e to the power t many particles, and you look into the positions of these particles. So these things started with the connections of differential equations with probability. So one of the first pioneering works was this Fisher-Kolmogorov-Petrovsky-Piskunov equation, or popularly known as the FKPP equation, which was more to study population dynamics, where U, so this is U is a function of two variables, space and time, but here this plus U would denote the birth of the generation, and minus U square are the deaths, And there is a diffusive term which is the delta square uxt under certain boundary conditions. And initially people wanted to study the solution of this. What it turns out to be, it was a very interesting work by McKean in 1975, that if you look into the branching Brownian motion, and if you look into the positions of those particles, and you look into the tail of the distribution of the maximum of this, so it's a function of utx, then this utx satisfies the FKPP equation. So that's the link with the FKPP equation and the branching Brownian motion. And another celebrated result of Bramson in 1978 was that if you take a factor mt, which is like root 2t minus 3 by 2 root 2 log t, so there is a special interpretation of 3 by 2, but I won't go into that now. But if you plug in this solution, t plus x comma m plus mt, then it converges to a wx. And this wx is also interesting because it solves what is called the traveling wave equation. So this is the traveling wave equation which is which was shown to be satisfied. Now, here comes another remarkable result by Lele and Selke, who showed that the traveling wave solution has a very interesting interpretation in terms of a distribution. So if you look into, so if Z was not there, this is just a Gumbel. Gumbel distribution is one of the extreme value statistics. So, and if you shift by a random variable Z, then, and look into this distribution now, Wx is a solution of this traveling wave equation. And Z is coming from the derivative martingale. When we finally state our result, this form will come back to this form of the result again later. But I just want to initially tell you a bit about the history. So then people wanted to study not only the maximum, but also how the whole point process behaves. And there was a long gap between these results. And in late 2000, around 2010, 8, there was lots of work by Bouvier and Argan and Kistler. And finally, these two groups like Bouvier, Kistler and Argan, and Eidekon, Brunet, Beristiki, and Xi, they could prove that for the branching Brownian motion, if you recenter the positions of the particles, then it converges to a point process L. And they gave an explicit description. And L has a very nice interpretation also, what they called is superposable. And the term was actually coined by Brunet and Derrida when they were studying some numerical features of the branching Brownian motion. They came up with certain stability properties of these branching Brownian motions, and they turned out to be true in this setup. We'll come to this again. Just to recap, so this was the continuum version where the time of splitting is continuum. If you go to the discrete case, which is the branching random walk, which I first described, it was initially started by Hammersley, Kingman, and Biggins, all independently, who were studying the topmost particle, the maximum of the topmost particle, and later in 2009, the order of the expected maxima was derived by Adario, Berry, and Reed. Bramson and Zeitouni proved the tightness of the recentered maxima, and it was finally in 2013 by Eidekon who proved the maximum converges to, again, the shifted Gumbel, which I showed, or the minima. Here they considered certain assumptions where minima was more suitable to consider. The minima converges to a shifted Gumbel, and which relied on the Z, which I showed you like just few. This Z was coming from derivative martingale, and there also this Z appeared, which relied on the works of Biggins and Cipriano in 2004. And finally, in 2015, the point process convergence was derived for the branching random walk in the boundary case. But just to now tell you what the setup in which we are working. So all these results had displacements which were light-tailed, in the sense that the distributions of those displacements had exponential moments. But when they have heavy tails or a power law, things are behaving a bit differently. And the maxima was initially studied by Duret in 1979 and 1983, which relied partially on works of Bramson also during that time. And we took up this case and we studied the point process convergence in the case where you don't have exponential moments of the displacements. So let me come to now what are the assumptions on this. So there are two things. So there is a branching mechanism and there is a displacement of the point process. So there will be two sets of assumptions. First, what are the assumptions on the branching mechanism? We know the branching mechanism is a Galton-Watson tree. We want it to be, first of all, supercritical, not to die out. So it should have a mean which is more than 1. So mu will denote the mean of this, this branching variable. For this talk, we'll assume that the tree which is formed, it doesn't have leaves. But for we have much more general result where leaves can be allowed. But for simplicity of presentation, we don't allow leaves. And what we also know that if you look into Zn, which is the number of particles in the nth generation of the tree, Zn by mu power n converges to W, a random variable W, which is non-negative, almost surely. And we assume this Kestenstiegem condition. So I'll come back to, in the last slide perhaps, how to even get beyond Kestenstiegem condition, that you assume the Z1 log Z1 is finite, which ensures that the W is strictly positive with probability 1. So why this W will be important is, in our case, we'll also have certain things like, which will be replaced, the derivative martingale will be replaced by something else, and there we'll need this condition. And what is the point process L we want to start with so that we can allow the power law displacements? So first of all, our point process will look like this, that it's delta of xi. Delta means it puts mass 1 again, it's a Dirac delta notation. So delta of xi, and you look into just up till Z1. Z1 is the branching random variable. And you assume the branching is completely independent of these displacements. So branching will always assume, because that helps us in working, we'll assume the branching is completely independent of the displacements. So Z1 is independent of x1, x2, which is we'll assume to be, for this calculations or the statement of the results, we'll assume that they are non-negative power infinity valued random variables. And each of these xi's will follow regularly varying minus alpha. So what do I mean by that? That if you look into probability of x1 greater than x, then it will be like x power minus alpha. So this is a slowly varying function. You can think of it as a log x kind of a function. So we'll assume that xi's are regularly varying minus alpha, and we'll assume this vector, which is 0 infinity valued, 0 infinity power 0 infinity valued random variable. So this is a sequence space. So we assume a regular variation on this space. I won't go into details of how to define regular variation on this complicated space, because it's complicated because it's not locally compact. So it's a complicated space. But let's, for this talk, let us assume that all the xi's we have, all the displacements we have are independent. Yeah.
So xi's are the displacement of the position.
Xi's are the displacement. So so the position will be the sum of the displacements, kind of, if you are on the positive side. So xi's are the displacement variables for me. So we are looking into this point configuration. We rescale it by Cn. So what should be the Cn? Cn will be something like so it should be asymptotically mu to the power n by alpha. So mu power n, remember mu power n is the number of particles in the nth generation. So if you just take a 1 by alpha root of the number of particles in the nth generation, the growth is like this. There is no centering involved in it. No, you don't need any centering of the positions. So you just look into Cn inverse SV. Then this random point configuration converges to a Cox cluster process. So this is a point process which is, so if you look into the representation, this is the independent case representation. There is much more complicated representation in terms of when you have dependence. So what does this mean? If you forget the W, then you see that these JL points, so I'll say what JLs are, these JL points are repeated TL many times. So there is a clustering effect which is coming in this process. So that's why it's called a Cox cluster process. And so what are these JLs? So these JLs, will come from a delta JL, so maybe I call it lambda, which will follow a Poisson random measure with intensity mu alpha. So what does this mean? So this is again a point process. It just means that if you take a set A, then lambda of A is Poisson distributed with parameter mu alpha of A, and if you take A1, A2, AK disjoint, then lambda of A1, lambda of AK are independent, and mu alpha of x infinity is like x power minus alpha. So this is a Poisson random measure with respect to the intensity mu alpha. So you take points from those point processes, those are those JLs, and you multiply them with this random variable W. W is, remember, is coming from the martingale convergence, that the number of particles Zn by mu power n converges to W. So that's the W which comes in out here. So what are these TLs? So I'll go to the next slide to make sure, like, make life easy to understand what.
Is there a non-trivial mass at 0?
Of this in star. Yes, at 0 it kind of blows up. So you take sets which are away from 0, like otherwise things blow up, because you have this intensity, you see, like x power minus alpha. So you have to be a bit away from the 0. So your sets are bounded away from the origin. So if you look into, so what the TLs are, it's better to look into a more simplified case where you have just, the tree is binary. In case of the binary tree, these TLs turns out to have a very nice interpretation, which is 2 to the power gk, where gk's are just IID geometric random variables with parameter half. In case of a DRE tree or a or a more than tree, you can already guess like what the parameters you have to replace. It's just 1 by mu to the power gk, which will come. So this is the representation for the process which you get in the limit. But when you have, so we are looking into these trees. Although the point process of this tree is independent of the this tree, of this, if you look into these two children's, this thing is independent of this thing, but there is huge amount of this dependency in between the children of the same parent. You can assume that. So this result would be true even if you assume there is huge amount of dependency between the children of the same parent. And then this representation is non-trivial. So one has to rely then on what are the stability properties of this point process which come in the limit. And there comes, so before I go into that complicated setup, one of the consequences of this representation is the maxima, the topmost particle. It's an immediate consequence that if you look into the position of the maximal position of the energy generation particle, then it converges to this shifted Frechet. So you remember, like in the light tail case, the limit was C. So it was like a shifted Gumbel. But here you have a shifted Frechet. And
the dependence of the displacement is hidden in this constant. All the dependence is there because you have not told us what exactly you're assuming about this.
No, the dependence comes in directly if you calculate, even in the dependent setup, the dependence comes in through a dependence measure in the C.
Yeah.
It's hidden in the constant. Sorry, I said shifted, it should be like scaled. I should use the word scale. So when we have such kind of a dependence situation, this theorem turns out to be true, and whatever the dependence measure we give out here appears completely in this constant C. But the form is exactly same. So Duret also, under different kind of assumptions, proved this maxima, and recently there has been extensions when the Galton-Watson tree is also like it is more like a multi-type Galton-Watson tree. A similar kind of result for the maxima also holds true, and the point process also holds. So let me come to what I was saying, that in the this limit has a very nice stability description that also appears in the branching Brownian motion case. So to define stability, let me recall few notions from point processes. So I use this circled notation, A circled P, where P is a point process, to mean that to each of the configurations I just multiply a scalar A and look into the this is the scalar multiplication on the space of on the point processes. And when I write sum of 2 point processes, I mean just superpositions. What does this mean? That I take 2 point processes, throw all the points together and look into the joint point process of this. So L1 plus L2 means that you're taking the superposition of the point processes. So this is interesting connection with a result by Davidov, Molchanov and Zuev, who made this definition for stability for point processes. So they called a point process or a point configuration N to be strictly alpha stable. So alpha is a parameter which is more than strictly positive. If you take 2 positive constants A1 and A2 and you look into this identity. So you take a point process N and you take independent copies N1 and N2 of N. For the first point N1, you multiply each of these point configurations by A1. For the second point process, you multiply each of them by A2. And you look into the superposition of this joint point process. It turns out to be, it's another point process with a scale factor which is A1 power alpha plus A2 power alpha to the power 1 by alpha. If this happens for n, for every A1, A2, then we say that n is strictly alpha stable. So this is exactly stability of random variables in the space of point processes. This is just the analog of that. What is interesting is this connection that we know that how, say for example, if you have a strictly alpha stable random variable, we exactly know how the characteristic function looks like. It even has a series representation which is the Lepage series representation. So one asks what kind of representation one might expect when you have a point process which is alpha stable also. And there is a nice representation which comes in this form, that it looks like a Cox cluster process. But so let me define all the things. So n is a strictly alpha stable process if and only if n can be represented as the sum of, so this is a sum means it's a superposition of these quantities. So what are these lambda i's? Lambda i's are such that they come from a Poisson random measure which I described out there. So lambda i's are exactly the Poisson random measures I described out here. And there exists a point process P and independent copies of Pi's such that n can be written as this. So this, if this representation, if n has this representation, then you can say n is alpha stable. If n is alpha stable, that is the previous properties hold, then you can show that there exists a point process P such that it can be represented exactly as this. Yeah? P. P is it's an existential proof. They don't give an exact construction of P. So if I give you, no, there exists one point process, there exists one point process P such that you can write it in this form. It's the proof doesn't exactly give you how the P looks like. So so the analog of superposability in this case is, so it's the same thing here. Remember, so the only difference which comes in from the light-tailed and the light-tailed case is that we are multiplying everything. In the light-tailed case, you have to shift everything. So if you remember, I was centering in the light-tailed case. I was saying theorems where I had to subtract something, and here I'm scaling things. So only difference is that you have to be, one is when you are in the light-tailed case, you have to shift things, and when you are in the heavy-tailed case, you have to scale things. So
light-tailed case also, you had a shifted gumball or a scaled gumball?
It's a shifted gumball because you put in the z up, x plus z log z kind of a thing. It's a shifted gumball. So what you look into is, so n star, if you look into n star, if it has a representation of this form, that if you take q to be a strictly alpha stable and w is the original branching random variable we had, the limit of the zn by mu power n, and you take the 1 by alpha at the root of that and you do the scalar multiplication, then this n star is equivalent to having again an analogous representation I showed in the previous slide. So if q is, if this w was not present, then it already has a representation by the previous result. If you shift it, if you now further shift the strictly alpha stable positions by a w random variable, then you again have an analogous representation. And this is true for the limit n star which is there. So once you can show that this representation is valid, you can exactly get how the limit looks like. And this was the idea of Brunet and Derrida for branching Brownian motion on how to identify the limit point process. So these two are kind of equivalent, and in the light tail case, this was recently shown also by Subhra and Zaitouni, who proved that there is a similar kind of decorated point process representation for superposable things, superposable point processes. So yeah, so how much? Okay, I have just 4 minutes. So before, just to give you a brief idea on how to do things in this. So there is one result so why is this superposable important? So what we do in this tree kind of calculations to find out the point process is, so we are in the nth generation. What we do is we look into the k steps before and cut down the tree at some point. So what you get is some number of, it's a collection of forest you get. So you get all independent trees. So each of them you think of as like coming from certain point processes. So this one, all these are hanging. Now you think of all these being, so you think of when you want to consider the total configuration, you recursively try to go into each of these configurations and superpose them. So you took a sum of all these cut trees. And then you think of that whether there is, for the heavy tail case, whether there is an analog in the point process level for a CLT or the extremes. So how do you prove the CLT or the extremes? So that's how this, there is this approach which comes into picture, that there is a domain of attraction theorem which comes into play, that we know, first of all, we know the set of all point measures is a nice complete separable metric space, and it has a nice metric. And one can define, again I'm not going into the definition, one can define regular variation on these space of point measures. So you can define when does a point measure, I can classify them as heavy-tailed. So that was the kind of work of Hult and Linskop who defined. So what you can show that if your point process is heavy-tailed in certain sense, forget the sense I have written here. If your point process is heavy-tailed, then you look into the superposed sum. That is the sum of these point processes up till n. Then you do a scaling by Bn inverse. Then it converges to strictly alpha stable point process. So this is the superposable, that you take the superposable sum, you scale it by Bn inverse, it weakly converges to a strictly alpha stable point process. So coming back to this result, that if you think that each of these trees are heavy-tailed, what you do is you superpose all these trees together. Then what you get in the limit is a strictly alpha stable point process. And what we know from the result of Davidov, Zuev and Molchanov, that the limit of the strictly alpha stable point process has a decorated point process representation. So you exactly get the representation for the limiting point process. So this approach is bit or say completely different from what happens in the light tail case, because in the light tail case there are much more complications which arise. When you have power laws, life is a bit more simpler and things are easier to deal. So just to finish off the talk, there are some further extensions. So one question which is that whether there is a continuum analog like the branching Brownian motion for this branching random walk, which is heavy-tailed increments. In the branching random walk, one crucial thing, branching Brownian motion, one crucial property is that the Brownian motions have nice Markov properties, strong Markov properties. So that is crucially used. So what kind of processes in the continuum time might represent such a heavy-tail process is, I'm unaware of it. So if you are aware, then we can discuss about it. Okay, also we saw that in the light tail case, the solution was satisfying in certain manner. The distribution function, the tail of the distribution function was satisfying the Fisher FKPP. So is there an analog, heavy tail analog of the Fisher FKPP equation? That's a kind of a, it's a question which many people have asked me before also, like whether there is a heavy-tailed analog for the Fisher FKPP equation. The idea would be to perturb the distribution function a bit and then see how the differential calculus behaves in that fashion. But yeah, I'm not sure how the equation looks like, so it's still an open question. Now we assume that the branching random variable has an infinite mean, finite mean. So the question is, what happens when you have infinite mean? So I'm yet to completely convince myself, but one of my master student has came up with a brilliant answer for this. So there is no shifted Gumbel in this infinite mean case. One of the reasons is that what it turns out that the nth generation particles are huge. There are lots of particles in the nth generation. So if you compare the number of particles in the nth generation with the n-1 generation, it blows off to infinity. And it blows off to infinity in a very fast way. So what it matters is, the point process doesn't see what has happened before. What it matters is the final generation. And things behave just like IID. So you get just the IID point process which is back. It's a very nice observation by the student, but maybe in future we'll come up more with the result. And there are also cases how to deal with the large deviations questions for the maxima and all these cases. And the critical case also, where there is some information in the critical case. So thank you for your attention.
In extreme value, you have also a third class, right? It's Weibull displacement.
Right, Weibull.
So in this case, suppose your displacements are bounded, and do you expect that your...
Yeah, it should be. We are expecting a similar kind of, like whatever happens in the extreme value, classical extreme value theory, a similar kind of thing to happen out here also. Because the proofs are very much influenced by the classical extreme value theory. So that's why that domain should also arise. But since it's kind of said not very interesting, so we didn't deal. So first of all, it's not very interesting. Second is, if you, so the Weibullian class can be related to the Frechet class. If you do some kind of a subtraction around the finite support which is there, then you can again get back regular variation. So roughly, it's an idea that you can again do things using the regular variation class for the Weibullian class. So that's why we didn't go into much into details of this. Yeah.
So regarding your second question, what if there's an analog of the FKPP? So are you expecting some sort of non-local?
Yeah, it should be a non-local kind of a, so the PD is not very well defined. If you do just brief back of the envelope calculations, you see that you'll end up in some kind of problems which I don't know immediately how to deal with them. But it seems like it's a very valid question which many people have asked me also, like what is the analog of the FKPP equation out here in this case? Yeah, but we have to assume a bit on the, so what you assume is Z1 has some kind of a regularly varying alpha tail with alpha less than 1.
Well, it turns out that in the infinite mean case, a former student of mine worked on that problem and showed that log Zn grows exponentially fast.
Right.
Zn is super exponential.
Yeah, exactly. No, that's the result we are using. Like Zn grows super exponentially. So that's why when you compare Zn with the Zn minus 1.
True, but then there is enough going on so that there is some kind of a stability for the associated random walk that you are just.
Okay.
That is what I would anticipate happening. So it's not hopeless.
No, it's not hopeless. But we have, I just said that we have started it. So it's a very recent master student who has observed this, and we have started it. So in future maybe we get more results. So thanks for your comment.